Thank you very much. A couple of words before going into math. So first of all of what I'm going to talk about comes from a collaboration that began, well, now almost 2 years ago, I guess, in Toronto during a thematic semester on no-smooth geometry. And this collaboration involves Tobias Beran, Matthias Braun, Matteo Calisti, Robert McCann, Ohanyan, Felix Rott, and Clement Saemann. I mean, many of whom are here. And so the starting project we had in mind was to try to understand splitting type results in no-smooth Lorentzian setting. I guess it's fair to say that we are really nowhere close to that, but still we have something I think that we can, potentially interesting that I want to share with you today. And another thing that I want to say is that well, first of all, I'm not an expert in Lorentzian geometry, and I don't pretend to be. And also, novel does not mean better. Okay, it's just novel. Okay? So maybe it brings something interesting. Hopefully, let's see. So here is something. No, it's not something. Here is something very basic that I think we can all agree on. So whenever we do, geometric analysis on RD or Riemannian manifolds, we tend to encounter rather often concepts like Sobolev functions, elliptic operators, Banach spaces. Okay, just as a sample, in both the talks that came before me, all three of these objects already appeared. Of course, I'm not saying that you have to work with this, nor that if you know how to handle these things, you're done. So that's just in a sense a set of standard tools, our hammer and screwdriver and so on and so forth. Now, the starting observation that everybody knows, but I really want to emphasize on, is that if we replace, it's really not clear what any of this is in Lorentzian signature. Okay, so say that you replace your metric tensor, Euclidean metric tensor. No, I don't want to update this now. Say that we replace the Euclidean metric tensor with the Minkowski one. Well, then the Laplacian is basically replaced by the Lambertian, and it's not anymore clear, what. And this is certainly not elliptic. Okay, it's not clear what a Banach space, say, of vector fields is. On RD, if we have a space of vector field, we can certainly know, what is the L1 or LP norm or something like this. This is totally unclear in this setting where this thing can be both positive and negative, among other things. And then, of course, one can wonder, well, those three objects that I mentioned are very useful in, elliptic signature. So what happens in this Lorentzian? Should we totally get rid of this, or is there any sort of replacement that we can, work with? Knowing that the fact that these objects, and I want to be extremely clear, the fact that these objects turned out to be useful in, say, in Riemannian geometry has no implication about their potential use in Lorentzian geometry. Maybe it's a different geometry, maybe you need a different set of tools. Nothing will be more normal than that. But, knowing this, it's certainly worth to pose the question a little bit. And okay, so this is what I'm going to talk about. So a little bit of introduction to Lorentzian geometry, and then I will discuss what these three things could be in this signature. And in order to emphasize similarities and differences between the elliptic and the hyperbolic setting, so basically all my slides will be divided into two. So in the top part, there's going to be the Riemannian or elliptic word, and in the bottom part, there's going to be the Lorentzian hyperbolic word. So in Lorentzian signature, there is something negative, something that is below zero. So below zero is cold, so I gave it a cold color, and above zero is certainly warmer, so that's why there's a warmer color, so we can, be sure about what is what. All right, so flat case. So the model case for, the elliptic scenario is RD, and we know everything about RD, right? We have the Euclidean norm, we have the ball, which happens to be round, so it's convex, it's compact, and is of finite measure. And we have the beautiful triangle inequality that, of course, in the long run, in some sense, if you want, that's the long run gives rise to the triangle inequality in metric spaces. That is, so metric space is basically some space where the triangle inequality happens to be true, in some sense. Now, what is the flat case, the model case in the Lorentzian geometry is the Minkowski space. Minkowski space is just, if you want, RD plus 1. With this metric tensor, let's agree on the signature. We have to agree. So where we will put the plus? I put the plus on the first guy, and then minus on all the other coordinates. And from the perspective of say special or general relativity, it's good to. I think it's worth to think about that. If we are sitting on 0, the directions we are allowed to move toward to are really just the positive ones. So we have a positive cone made of vectors with positive norm in some sense, and we call one future cone, the other one past cone, and we are only allowed to go in the future. So in some sense, this is kind of the directions allowed. And the unit ball, whatever you want to call ball, the bottom line or the up line of this, this hyperboloid, it's neither convex. Well, it could be convex, but it's never compact nor of finite measure. Now, one important thing, really crucial, is the following. In this future cone, this GMVV is positive by definition, and if I take the square root, what happens is that as this satisfies also a triangle inequality, it just happens to be reversed. Okay, the reverse triangle inequality is in place, and you also have a reverse Cauchy-Schwarz inequality. Right? So that's the flat case. Now the manifold case is built upon this flat case. Riemannian manifold, I guess again we know everything about them. I don't want to spend my minutes into describing what a Riemannian manifold is. Perhaps let me just emphasize what a Lorentzian manifold is in the setting or that I care about. So a Lorentzian manifold is a smooth manifold where in each tangent space I have a Minkowski norm, and this is time oriented. So it means that I have a consistent way of choosing future at every point, and plus. There is some assumption that, so in some sense I want to say when a Lorentzian manifold is, say, complete, right? So, and in the Riemannian setting, I would say it's complete as metric space, and then Hopf-Riemann theorem would tell me that this is equivalent to geodesic completeness and a bunch of other stuff. In the Lorentzian setting, the matter is more complicated. There's the whole so-called causal ladder it's worth to be investigated. For the perspective of my talk, I will assume that the strongest possible assumptions on the table. That is to say, there are no closed causal curves, so it means it cannot be the case that I start from a point, I go to the future, meaning I follow a curve that has tangent, direction always in the future, and then I happen to, come back to my point once again. That would, in some sense, defy the law of causality in a physical sense. And I also assume that causal diamonds are compact. So take 2 points, look at the future of one point, the past of another one. This set should be compact for any couple of points. Okay. And so one thing that one could do in such a setting is, well, first of all, realize that geodesics that can be defined through the geodesic equation, grad nabla dot is equal to 0. This is a purely differential, is an ODE. Okay, and geodesics are locally in the Riemannian setting are locally minimizers of the energy for whatever exponent q bigger than 1. And it turns out that in the Lorentzian setting, geodesics are locally maximizers of the kind of the same energy, except that now q is smaller than 1, possibly negative. Okay. And once you minimize or maximize, in this case, you maximize the energy, what you end up with is this function L, whose value is independent on q, much like the value of the distance between x and y above is independent of the parameter q. And it defines a function that, well, no surprise, it satisfies the reverse triangle inequality, because this is sort of the carved version of the reverse triangle inequality that we have on Minkowski, right? And this triangle inequality above is what defines metric spaces. This reverse triangle inequality below is what defines, Lorentzian length spaces, at least in the axiomatization, very successful axiomatization that Michael Kunziger and Clemens Saemann proposed a few years back, 100 years after the definition of metric spaces was to be pointed out. Now, all right, so that's it. Okay. Now let's discuss Sobolev functions in these two settings. And in fact, before discussing Sobolev functions, I guess we could discuss convex energies. So because among other things, when I have a Sobolev space W1P, even before knowing what a Banach space or a complete space, these sort of things are, I know that I take the function f, the map that takes f and the trans, say, integral of differential f to the power p is a convex function. Okay, and on top of this, I can build my Sobolev theory. So let's see how this works. picks p bigger than 1, say strictly bigger, and notice that the map that takes, say, a smooth function f and returns the modulus of the differential at any given point is a convex function, for trivial reasons, because we have the triangle inequality, on the dual of the tangent, if you want. And then you post-compose this function with this convex and increasing function z to the p over p, whose graph is depicted over there, and then the resulting composition is convex, and because of that, whenever you integrate this, you get a convex function that is lower semi-continuous once you properly define things in the non-smooth category. Can we do the same in the Lorentzian setting? Well, yes, provided we just restrict the attention to so-called time functions. So a time function is basically a monotone function. So on a Lorentzian manifold, in the way I just described, there is a natural order relation. I can say that x comes before y when there is a curve going from x to y, say smooth with speed points always in the future direction. Okay? And well, a time function is just a monotone function in this sense. The wording comes from general relativity because Lorentzian manifolds, they're supposed, according to Einstein, they are a model of our universe. Time is relative in our universe, so we don't have a universal clock, but any given time function can be thought of as a kind of universal clock, whose only property is that if the events y comes after x, then the clock it becomes signs some later hour. Okay. Now. As a consequence of the reverse triangle inequality in the future Conan-Minkowski space, it turns out that this function is concave. So that's really equivalent to saying that we have the reverse triangle inequality. And therefore, if we post-compose this concave function with the concave and increasing functions, z to the p divided by p for p smaller than 1, possibly negative, what we end up with is a concave function. Okay. So this is the concave function we're just alluding to at every point. Then I integrate it. I change signs because I love more convex function than concave. Okay, and we get a convex function that's now defined on the space of time functions. Right? Remark on RD, finite or Riemannian manifold finiteness of the p energy is a statement about regularity, among other things, as for instance, already I guess I mentioned in a talk a few minutes ago. In this setting, it is not the case. In some sense, every time function locally has finite energy. So this is really not a statement about integrability, but still we have a convex energy. Why do I care about convex energies? Well, because it happens to be the case that if you have a convex function, you can take for free at least one derivative. So a convex function is something that has two derivatives bounded from below. But so at least one derivative can always be taken in the sense of directional derivatives. So for instance, the P Laplacian can be defined or interpreted as a directional variation of this P energy. Okay? Right, so that's just a basic. So say that FG are smooth with compact support, that formula above certainly holds. And then analogously, if I play, now I have another energy in my Lorentzian setting, I can try to play the same game just to see what comes out. And what comes out is the p D'Alembert, okay? Where, so without this would be the D'Alembert. With the p D'Alembert, this term pops out. Okay? Why there's an additional minus? Well, because I put a minus in the energy, okay? For the records, and I'm, okay, I make a statement. So this definition, so I could pick this and the above as definition of what the P Laplacian and the P D'Alembert are. If I do so, the only thing I need to define P Laplacian and P D'Alembert is this thing modulus of the f, not even the differential, just the modulus. Okay. Therefore, and this is a big therefore, in some sense this sort of procedure can be applied in very general spaces, not necessarily smooth, in particular, metric measure spaces, either in the elliptic or in the hyperbolic sort of signature. And what we did with the octet, in some sense, was really to study bounds on the P D'Alembert in the non-smooth context. I'll give just one statement in the next slide. So this object modulus of the f in the metric measure space is what Neges mentioned as the upper gradient version of differential. And there's a long story, the actual definition. So actually, Neges was one of the founding figures in this matter. Shiger is another one. The Finnish school certainly played a major role, and this observation that so the modulus of the differential can be used to actually just that to develop a differential calculus at least up to second order is something I played a role with. All right, so what's the theorem I want to discuss? Well, let me just mention this maybe. So let's agree that this limit can be interpreted as the action of the p-Laplacian version of f applied in the direction of g. Okay, and so above, while above is the action of the p-Laplacian of f applied to the differential of g. Now, a standard theorem in Riemannian geometry, this goes back to Calabi, is that a lower Ricci bound implies an upper bound on the Laplacian of square distance. Okay, and this theorem has an analog in the no-smooth category. In this slide, there are a lot of things that I'm not really defining. So the theorem is about CD spaces, as introduced by Lott, Villani, and Sturm in two independent and very famous, rightfully so, papers, motivated by earlier studies of Cordero-Raskin, McCann, Mugerschlager, Otto Villani, Sturm, and Bornes. And this theorem below is formulated in so-called TCD spaces, as defined by Cavalletti and Andrea Mondino, who is here after studies of Robert McCann and Mondino and Sur in the smooth category. Now, so I really don't want to parse the theorem. What I want instead to focus the attention on is the following. First of all, this theorem, I mean, let's pick this when the underlying space is a smooth Lorentzian manifold. Okay, so I don't need to discuss too much about this TCD and the TCDQ conditions. And let me also what else? And yeah, so the underlying in this setting, the underlying assumption is that the Ricci curvature is non-negative in the time-lag direction, whereas in the elliptic setting, the Ricci curvature would be non-negative along all directions. And dimensionless for equal than n. This capital N is the upper bound of the dimension, much like in Theodor Stork. Okay, so in some sense, this theorem above could be interpreted, a variant, or if you want, rewriting Calabi's theorem. And this theorem below is actually a theorem about the p-Laplacian version of the analog of the distance to the power q over q in the Lorentzian setting. And okay, if you tell this theorem to any person working global Lorentzian geometry, it will tell you, well, let me look at what is this p-Laplacian version that you just defined, and they realize, okay, well, this is the standard D'Alembert result that is already known for time separation functions in the Lorentzian setting. But I really want to insist that in some sense, our interpretation is to think about this as a p-Laplacian version, and I come to back to that in a second. Yes, thank you. G is equal to, yes, I agree. Yes, in this page, yes, thank you. Which is maybe is the only page where rho appears, but yes, thank you. Sorry for the, thank you for pointing this out. Yes, surely. Yes, of course. This left-hand side, as I mentioned, is like the action of the P, the Laplacian of the D'Alembert of f applied to G, so that's really kind of an upper bound of the P Laplacian or P D'Alembert. Apologies. Thank you, Theodore, for spotting this. All right. All q less than 1. Maybe take out 0. I mean, 0, there should be a log in here if we put 0, but yes. So it works, provided we define what is CDQ. There is only one result which works. Okay. So yeah, but thanks. So in my theorem, I really only work with the case P Q equal to, which is the one that works better. Here I brought in generality just to highlight the formal similarities between the two statements. Okay. And I'll have at least one more comment about these similarities. All right. Okay, so in some sense, that's all I wanted to say about Sobolev functions. Now discuss elliptic operators. Yeah. So in fact, my talk is this slide. Okay, the rest is motivation behind and discussion around this. So the D'Alembert say, even in Minkowski, okay? There's no need to go into the carved case, even in Minkowski. The Lambertian dgt minus Laplacian in the x variable can certainly be written as divergence of the gradient, where the gradient is the one given by Minkowski signature, right? So a smooth function as a differential, you use the metric tensor to turn the differential into a vector field, and that, the role of the metric tensor, appears, and then you take the divergence of the vector field, and according to the signature of the metric tensor, you get either Laplacian or D'Alembertian or whatever else, depending on the signature. And what we are saying is that, wait a moment, rather than studying D'Alembertian, at least the P D'Alembertian for P smaller than 1 pops out naturally in our setting. Okay, and the D'Alembertian is certainly an elliptic operator, but to our surprise, this P D'Alembertian is elliptic, at least on time functions. Okay, which is the only set of functions where it possibly could be defined, because there is this term modulus of the f to some power, and that you can only give a meaning if the modulus of the f was non-negative. So some regularity in the sense of time, regularity of the time function should appear. How do I know that that is elliptic? Well, I did a computation, but I could avoid doing the computation and just notice that that P D'Alembertian arises as subdifferential as first variation of a convex function, and therefore, that must be elliptic by nature, right? So it is worth to notice. It is worth to notice that if we work with the Lorentzian distance, this time separation function L, then much like the differential of the distance is 1 whenever defined on the Riemannian manifold, the differential of this Lorentzian distance is 1 whenever defined in Lorentzian manifold, which implies in particular that if you only care about the Lambertian of these guys, you will not notice the difference between these two. Okay? And in books about global Lorentzian geometry, the Lambertian and the Lambertian estimates often appears regarding this object, the distance over time separation, sorry. Right? And surprising results, to me, and I will mention one of these, can be deduced out of the Lambertian estimates on global, in the setting of global Lorentzian, Lorentzian geometry. And the fact that this D'Alembertian actually coincides in this set of functions with an elliptic operator, to me, serves as an explanation of why this sort of comparisons result are in place, because typically comparison results, call for ellipticity rather than hyperbolicity. Of course, that's just me. I mean, the results are there and they've been proved already in the literature, they're famous and whatever. So people working in the field, maybe they couldn't care less. But it is interesting to me as a sort of coming from the elliptic framework to notice this fact. And in fact, now there are so many analogies between this Riemannian and Lorentzian setting that maybe one can start wondering whether there is a common ground between the two. And I think there is. And in fact, it's not me that I think. So Agrachov has been pushing this for at least 25 years, and a topic that has been also reworked more in the setting of Rich lower bound by Shinichi Ota, who also is here, 10 years ago. And the point is that basically we can make a case for studying comparison Hamiltonian geometry. So all of what I said can be, in some sense, condensed into the following observation. Well, in elliptic signature, for p bigger than 1, that functional italic p bigger than 1, the function that takes a covector and returns norm to the power p over p is a convex Hamiltonian, right? And the same is true in the Lorentzian signature, provided now we take p smaller than 1, we put the Hamiltonian plus infinity when we are not in the future cone, and when we are in the future cone, we get that, right? Now, so just as a couple of examples of things that you can do when you have a convex Hamiltonian, and then here I'm rephrasing Agrachov and Ota in a very, very condensed matter. But first of all, Hamiltonian, you have a natural Lagrangian associated by Hamilton-Lagrange duality. And once you have Hamilton-Lagrange duality, you have another way of transforming cotangent vectors, like the differential, to tangent vectors, like you would do when you have a metric tensor. You just, you say that the gradient is that, or the Hamiltonian gradient is that vector for which that equality holds. And under some smoothness and strict convexity assumptions, that vector is unique. And let me not care about what happens when it is not unique. Now, The P Laplacian or P D'Alembert is nothing but the Hamiltonian Laplacian, if you want, which is just the divergence of this Hamiltonianly defined gradient. Okay, and Ricci curvature along every future direction or future direction can be read in terms of a suitably defined bound on some Hamiltonian Ricci curvature that could be defined. Shinichi did. I'm not going into I will not give you the definition. Just believe me on this step. And a couple of things that are worth to notice is that well, first of all, okay, I didn't. Perhaps let me go back. Let me go back to this so that we don't get confused by a further statement. So the two statements about comparison for the P Laplacian or the P D'Alembertian, if you read them in the Hamiltonian formalism, is really just one statement. Okay, so this Hamiltonian formalism is really something that captures both kind of behaviors at the price of giving up the linearity of the D'Alembertian. But certainly it's certainly interesting to notice that they are not two different things; they are the same thing. And another thing that is certainly very much worth pointing out is the following: is the existence in the very generality here of convex Hamiltonians of a beautiful formula that is a variant produced by Shinichi Ota of the famous Bochner identity, and it's a very nonlinear, but still is in place. And well, so first of all, it's written Bochner Ota, but the way you can interpret this is a kind of a Riccati equation. Okay, if you know how Bochner identity appears in the Riemannian setting, you can interpret it as a Riccati equation. Here you have a function f, smooth. I let it evolve according to the associated Hamilton-Jacobi equation. I take a curve gamma t, which is is flowing along the direction of the Hamiltonian gradient. I differentiate the Hamiltonian Laplacian in ft at gamma t, so that in the Riemannian setting p equal to this is the gamma 2 thing, a way of writing the gamma 2 thing. And this is equal to, to the sum of these two terms. And what is interesting is that, well, first of all, this Ricci guy appears here, the same that is defined, or that I did not define, but Shinichi did above. And this term really has an elliptic flavor, meaning this guy is always non-negative, and it is zero if and only if something extremely rigid occurs. In this case, the function f should be affine along the Hamiltonian flow. Okay, why is this interesting? Well, the Bochner identity, you have this for any metric tensor, for any symmetric tensor, regardless of the signature. Okay, the problem is that if you don't have positive signature, if you're not a Riemannian manifold, but say in a Lorentzian one, the analog of this squared Hessian term could have a sign, could be both positive and negative. And now the use that you make of the Bochner, or the typical use that you make of the Bochner identity just falls apart. No? Typically, you use the Bochner identity to deduce some upper bound on the Hessian. In your dream scenario, the upper bound of the Hessian is zero, so therefore the Hessian is zero. But if this guy has a sign, knowing that it is less real than zero really tells you nothing. Let me give you a sample case where, sort of, in a sense, this program of reformulating Lorentzian geometry in this Hamiltonian formalism and emphasizing and using this ellipticity of the P D'Alembertian can really help. So here is an example of a rigid result, perhaps the prototypical example of rigid result, at least in the setting of lower Ricci bound. It's a theorem by Chigre and Gromol. It has a long history. It comes from a theorem of Combosen who proved it in 2 dimensions. I don't want to get into that, but so in the lower Ricci bound case, the theorem is the following: take a manifold with a negative Ricci, and say that it contains a line. So it is a geodesic which is infinitely long. So you have an embedding of R isometric in the manifold. Okay. Well, then something extremely rigid happens, namely your manifold is actually the product of that line times another n-1 dimensional manifold that also happens to have a non-negative Ricci, right? So that's the splitting. So the manifold splits as a product. Now, there's an analog in the Lorentzian signature. The theorem has been proved, in various papers according to the kind of underlying assumption that one puts in the Lorentzian manifold, and at least the paper of Galloway answered a conjecture by Yao, and the conjecture was the following, or the theorem, if you want, is the following. Now, take a Lorentzian manifold. Suppose that you have non-negative Ricci just in this future direction. I don't care what happens in the in the direction where the metric is not positive. And suppose that it contains a time-like line. So there's if you want an embedding of R, an isometric embedding of R, in this sense that, in this sense. well, then the manifold splits as well. And it splits as a product of, now having Cauchy product, if you want. So the signature that you put in this product is dt squared minus gn. And yeah, and that's it. So it's very much analog to this. And to me, it's a wonder that they've been able to prove this theorem. I mean, if you look, the proof is marvelous. It's really marvelous. And it's incredible that, despite the fact that they're working with an hyperbolic kind of object, they managed to obtain this rigid result. It's really, I mean, it's worth, it's really worth to be studied. Now, what I want to point out is that with this sort of idea of replacing the Lambertian with P Lambertian, we could, in fact, redo the classical elliptic proof with basically, at least formally, without any change. So let's go through it. So first of all, how do you prove the splitting theorem? Well, first of all, notice that a manifold splits as a product if and only if. That is an easy statement. If and only if you can find a non-constant function with zero Hessian. Okay? So that's the point. If it splits, then the non-constant function would be the R coordinate. Okay? If you have a function with non-zero Hessian, you just take the gradient flow of that function, and that instance that produces the splitting. The Riemannian case. In the Lorentzian case, the same, except that given that there is some time consideration to take into account, this non-constant function with null Hessian should also be a time function. It should be increasing. Now, whenever you have this situation, whenever you have a line, you can always define the so-called Busemann functions, which are a kind of distance from the point at infinity, above or below along these lines. So you just look at these limits over there, and by basic consideration about triangle inequality, this limit exists. This limit exists, and in general, regardless of curvature bounds, this b plus, so this limit when you go to plus infinity, is always above b minus, and they are equal along the geodesic. And kind of the same happens in this Lorentzian signature. Okay? And if you are familiar with maximum principle, maybe you already know where I'm heading, or maybe where Cheever and Gromol were heading to. So if you have a negative Ricci, then Laplacian comparison is going to tell you that this Busemann function have, b plus has negative Hessian, b minus has positive Hessian, but they agree. One is above the other, and they agree somewhere. So by the strong maximum principle, they must agree. Okay. So now we have an harmonic function, non-constant harmonic function. We plug it in the Bochner identity. The left-hand side is 0. The right-hand side is non-negative by sign consideration that also involve the non-negativity of the Ricci. So the Hessian is 0, and so the function is our function with 0 Hessian that we're looking for. What do we do in Lorentzian signature? The same. Okay? So non-negative Ricci implies by Q Lambertian, P Lambertian, okay, that this Q Lambertian of the B plus and of B minus have the same sign consideration that we have in the elliptic case, up to some technicality that can be dealt with. We can apply the strong maximum principle to use even in this case. I think, actually, strictly speaking, this is called the tangency principle, strong tangency principle. The operator is not linear, so I'm having a function that is sitting above the other, and with this, relations between the elliptic operators, and so they are tangent. And then therefore tangent with the correct inequalities, and therefore they agree. Now what do? Well, I plug this in this Bochner-Rott identity, and again, by basic consideration, I can see that this left-hand side must be identically 0. What about this right-hand side? Well, this is not negative because it's also not negative. This is not negative because it's the Ricci term. So as before, this term must be non-negative, but this Hessian term, Hamiltonian Hessian, being 0 means that the Hessian in the time-like direction is 0, and that's sufficient to conclude. Right? I forgot how much time. Is it still 10 minutes, or am I already over? 10 minutes. Okay, great. Okay, great. Thank you. Okay. All right. So in some sense, this. So first of all, this can be made rigorous, a subset of the octet. Being able to complete actually the proof, and is in some sense I consider it as a proof of concept of the validity of this sort of arguments involving the study of this pedal inversion in this Lorentzian setting. So it allows to make use of typical elliptic considerations in a world where these were not present. Let me mention that. So, for instance, what Galloway, Eschenburg, Neumann, and others have been doing to study splitting type of result in Lorentzian geometry, given this problem of design of the Hessian term in the Bochner identity was to basically study Bochner identity on so-called Cauchy hypersurface. So you sort of fibrate your manifold into horizontal slices, so to say. On these horizontal slices, you have an actual metric tensor, in the sense of these are Riemannian manifolds, and then you have a classically defined Laplacian that is elliptic, and maybe you can start working with that. And but in some sense, these considerations bypass this need. Now let me just conclude maybe with a couple of words about Banach spaces. So why do I care about this? Well, because our research project was motivated. First of all, why not? Banach spaces are kind of an interesting concept, and so our work was motivated by study in non-smooth Lorentzian geometry and functional analysis. In the classically defined metric spaces plays a major role, in particular in the discussion about RCD condition. The R of the RCD has a lot to do with Banach spaces, and all the functional calculus, the differential calculus, is based strongly on concepts, functionality concepts, and therefore it's only natural to try to see. Again, try to mimic what works, to see whether it works or not. In either case, it's a win. So either you understand that it works and you're happy, or you understand why it does not work and you're still happy, because then you learn something more about the structure of your spaces. So in some sense, if you want, so a basic question that you could ask for is the following. Take the collection of C-infinity completely supported time-like vector fields on Minkowski. Do they belong to any naturally defined Banach space? On RD, I know, right? The answer is yes. You give me P, and I tell you that these C-infinity vector fields are in these LP spaces, for basically an EP. In this hyperbolic setting, I'm very much in trouble because the triangle inequality goes in the other direction. There's no way anything of that sort could work. And that's quite of an issue, right? Because the completeness of Banach spaces is really what allows us to prove existence results in high generality. Okay, so what do we do? So if we don't have complete objects when we work in the non-smooth setting, that's hard to to work on. So I want to make a proposal. And the proposal is the following. So a Banach space, we all know what it is. So it's a normed space. So an hyperbolic Banach space, I think, could be, first of all, a cone. So I want to give up the vector space structure. I'm giving up the vector space structure. And what I retain is possibility of taking linear combinations with non-negative coefficients. And I want this to be endowed with an hyperbolic norm. So something for which the reverse triangle inequality is in place, right? Now, a Banach space, of course, should be complete. Right? Complete means Cauchy complete. Okay, so sequences, Cauchy sequences admit a limit. Now, as I mentioned, nothing of this form can be asked at this level because, in Minkowski, this makes no sense. And what I think could work is, work with this causal structure in sense once again and speak about order completeness. So a cone naturally comes with an order structure. I can say that V comes before W if there is Z such that V plus Z is W. That why not? And the order complete means, so strictly speaking, means that directed sets admit a suprema. That's the correct definition. If you want to think about an increasing sequence, I must have a limit. So that's a good enough proxy for today. And of course, I'm really telling nothing new. I'm really telling nothing because this is really just Cauchy versus Dedekind completed. If we go back to real line, we have two different ways of speaking about, or at least two different ways of speaking about, completeness of reals, either in the sense of Cauchy or in the sense of Dedekind. And what I'm just pointing out is that the classical, Banach spaces are defined through Cauchy completeness, and this version is defined through Dedekind kind of completeness, or Dedekind related. There are many versions of Dedekind completeness, so upward directed sets supremum is the one I'm using. And let me just point out, so I want to, I don't have time, I just want to give you one example, hopefully convincing that there is something going on here, worth to be studied. And the example is the following. So the basic example of Banach spaces, the first one we met when we studied those, are LP spaces, right? You take P bigger than 1, and you take LP functions. So what could possibly be the first example of hyperbolic Banach spaces? Well, let's take P less than 1, Let's consider non-negative functions, possibly infinity valued, with this hyperbolic norm. Okay? It turns out, but maybe this already, we already know that this guy satisfies the reverse triangle inequality. Right? In fact, sometimes in books we find the LP spaces with P, say between 0 and 1, where then the kind of the norm of the wannabe norm is defined without taking the P root, because it said, no, if you take the P root, triangle inequality fails, and maybe it's a good thing that it fails, because maybe in this case, this regime, maybe we can't be interested in the reverse triangle inequality. And there are a few things that we can do. So first of all, there is an interesting, so if you want, parallelism. So the dual of LP, of course, is LQ when 1 over P plus 1 over Q is 1, and the duality map is that, the one that sends an LQ function G into integration against it. I have not defined what it is the dual of an hyperbolic Banach space. Let me do it here. So what's the dual? The dual would be the collection of maps L from our cone into, well, not R, but 0 infinity. That's in some sense morally our fields of scalar. Linear and suprespecting. So should be continuous, and is continuous in the sense of order, suprespecting, in the sense of order, in the sense of say Vn converging. The sup of the increasing sequence Vn is the infinity. Well, then L of infinity should be the limit of L of Vn. So in that sense, you encode the monotone convergence property in the definition. And then you can define the hyperbolic. So what's the norm of this guy? Well, in the Banach setting, in the classical Banach setting, the norm of an operator is the sup of L of V among all V with norm 1, right? Well, what will be here? Well, be just the inf of L of V among all the V's with norm 1. Okay? And with this definition, it turns out that the dual of LP, even in this setting, is LQ, okay? With the same looking duality map. Okay, and at least when P strict is more than 1. Of course, we know that P equal 1 is a little bit of an exception. So the dual of L1 is L plus infinity, where the norm of L plus infinity is the essential supremum of the function. Well, in this case, the dual of L1, this hyperbolic setting, is L minus infinity. Well, but the minus infinity norm is just the essential inf. Okay, and there's now that you study this, there is a natural case that pops out as sort of interesting, the self-dual case, when P is equal to, you have this, the dual of L2 is L2. In the self-dual case, in this hyperbolic setting, is essentially when P is equal to 0, and this is only defined when the mass is 1, in which case the L0 norm is the a geometric mean, if you wish. I'm slightly cheating here, but only slight, so I won't. There's a few technicalities, but that's essentially the point. And here is if you look at the picture of the unit sphere, so that is really what is happening. So we start, so the unit sphere in L infinity is just the square. Think R2 with the L infinity norm. Now decrease L infinity, and the square becomes rounder and rounder, and when P equal 2, we really have the ball. When P is 1, we have the diamond, okay? And if you let P go smaller than 1, you start seeing an hyperbole. Okay, and when P is equal to 0, for the first time, this guy becomes unbounded, and when you end up in the minus infinity case, you have this star shape kind of configuration. So it's really a continuous, right? And let me just conclude noticing that the L2 norm satisfies, of course, the well-known parallelogram identity. It happens the case that the L0 norm also satisfies a kind of nice-looking second-order sort of identity. So norm of the product is the product of the norms. I mean, the proof of this is trivial as the proof of the other one. I don't know why this happens. I really don't know. I mean, why? So that really looks like x squared plus y squared equals something, which is the circle equation. And this really looks like x times y equals something, which is the hyperbole equation. I don't know why, but that's the case, and I'm over with the time, so I thank you for your attention.